Welcome to Lecture 20. 3 more to go after this one. We ended Lecture 19 with one problem left to go. Problem number 4 on the practice. Now this problem is a review from the material that we discussed in Lecture 16 because we just finished talking about acids and bases in Lecture 19. Here is an acid-base equation called a titration. Remember I said in lecture 19 not to let this word scare you. It is the name of the lab technique, but it's still just an acid-base reaction, which means double replacement. And so we're going to work this problem. Sodium hydroxide, one of the ones you should know, one of your strong bases, is you're titrating it with sulfuric acid. Okay, something else you should know. Acid-base, double replacement, the hydrogens react with the OHs to make water. Notice I have 2 hydrogens here on sulfuric acid, so I am going to make 2 waters, which means I'll need 2 OHs. And then when I write the formula for the salt, which is the sodium and the sulfate together, I indeed needed 2 plus 1 sodiums to balance out the -2 on sulfate. All right. Material given in the problem question is volume here in milliliters. 0.121 molar is the concentration. And then we have 0.102 molar sulfuric acid, and we used 10 milliliters. Okay, so if you're not in moles, get there. This is a stoichiometry problem. A titration question is basically a stoichiometry problem. We are going to get into moles by taking that big M and rewriting it. Moles per liter. It's a ratio which always throws students off. So 0.102, I'll just do it right here. And then this volume, that's how we're going to get rid of the liters, is I'm going to switch that to liters. And then when I multiply, I should get 0.00102 or 1.02 times 10 to the -3. Okay, I am going to put that in on my calculator and just make sure, but I'm pretty sure that's what it would be. Yes, 1.02 times 10 to the -3 moles. Okay, then we will move to the species with the question mark times 2 over the 1 in front of sulfuric acid, so times 2, and I get 2.04 times 10 to the -3 moles. And over here, right here, I am going to use the molarity given to me, and since I'm being asked for volume, I'm going to flip the molarity over. So instead of writing 0.121 moles per liter, which is what that big M means, I am going to flip it over and put the liter on top and the moles on the bottom. And then multiply times this number of moles. That number of moles divided by the 0.121. And then if I want to go ahead and put it into milliliters, I'll just say 1,000 milliliters per liter. And my liters cancel. All right. So the 2 times 10 to 2.04 times 10 to the -3 divided by 0.121 and then times 1,000. And our volume is 16.86 milliliters. So again, same type of problems we did in lecture 16. Solution stoichiometry always gives students a tough time because of how unfamiliar and non-intuitive this whole molarity thing is. It is a ratio. So it has double units, and that always throws students off. All right, well, we just finished talking about acids and bases in lecture 19. Lecture 20 takes that one step farther to talk about pH. Now, I know you have heard a lot about pH over the years. You've probably maybe done some little purple cabbage labs or something like that in high school. But we're going to really look at it and learn how to do it quantitatively. This is a much more number-oriented lecture than the previous one, but of course, water is one of our basic substances. It's usually the solvent in these solutions. And one thing we have not talked about in terms of water yet is that water, you know, it can act as an acid and a base, and the word for that is amphoteric. So if I have two water molecules, as I have here in this diagram, one water molecule can act as so which one of these, the right or the left, is acting as the acid? It's the one losing the proton or the H+. So this water molecule is acting as an acid, the one on the right, and the one on the left is accepting that proton, so it is acting like the base in the Bronsted-Lowry sense. But it is also in the Lewis sense, because we've got Lewis acid-base definitions, because H+ is a really good Lewis acid, and we are forming that coordinate covalent bond with oxygen to form the hydronium ion. So when this happens, when this water molecule here loses an H+, what is left behind is the hydroxide. And this molecule, when it gains the H+, becomes hydronium. Okay? Now this is an equilibrium reaction. They're not showing it. The picture that I copied didn't show it as an equilibrium. The back reaction is happening as well. All right, so this goes on in pure water. So what is the concentration of H+ in pure water, and therefore should be the same as the concentration of, these should be equal to one another in pure water, because you can't generate one without generating the other. All right, so the concentration of the two should be equal. Well, it just so turns out that the constant for that reaction above is equal to 1 times 10 to the minus 14. In fact, this constant is always the same, hence it's called a constant at 25 degrees, even if the hydronium ion concentration increases. So the Kw expression is very useful. It means that you take the hydronium ion concentration times the hydroxide ion concentration to equal 1 times 10 to the minus 14. So let's say we had 0.1 molar HCl. So that this was 0.1 molar, the hydronium, because that was an acid we were just talking about. Well, in order to get, and I didn't know this, in order to get the hydroxide, I would take 1 times 10 to the minus 14 and divide, by 0.1. And that would equal my hydroxide concentration. So if I know one, I can find the other, because no matter how I change if I increase H3O+, then OH- must decrease, and vice versa. So it's a constant that where you can always relate those two to one another. Well, you know, doing 1 times 10 to the minus 14s and 1 times 10 to the minus 7 and so on, which is what at neutral pH, or when these two guys are equal to one another, when H3O+, if this is going to be 1 times 10 to the minus 14, then these two in pure water must both be 1 times 10 to the minus 7, because they're equal to one another. So, you know, using these scientific notation numbers is a little cumbersome. So what has been developed instead is the pH scale. And in pure water, hydronium and hydroxide are equal, and so we call it neutral. So if I take the log, and this is a log-based scale that we're going to use, if I take the log of 1 times 10 to the minus 7, I actually get -7. But if I do minus the log of 1 times 10 to the minus 7, I get 7. So when the hydronium ion concentration, and the hydroxide for that matter, are equal to 1 times 10 to the minus 7, the pH is 7, or neutral, because the OH- and the H3O+ are equal to one another, so they cancel each other out. All right? But if we changed one, then we changed the other one such that they still always, when you multiply them together, always come out to 1 times 10 to the minus 14. All right? So couple things to realize. I mentioned here about an acid, but I want to talk about an acid example and a base example. All right, so pH is a log-base scale, essentially, of the kW expression. Now, there are lots of different relationships here. So if I take this kW expression and I take the log of it, that's how we end up with this handy little relationship. So this is this one here and this one here that we have above in the notes as well, really are equivalent to one another. They're just, one is a log of the other one. This is the log of the top one. All right. Before we go on to talk any more about this, I want to talk a little bit about acids and bases themselves and what you get out of thinking about them. What does it lead to? So, for instance, let me write down a few substances. Oops. All right, so if I write down HCl, hydrochloric acid, and my concentration is going to be 0.5 molar. Sodium hydroxide, we'll make it 0.7 molar. All right. Let's do H2SO4, 0.6 molar. And let's do calcium hydroxide, 0.4. Okay, when you are considering, and these are all strong acids and bases, because really in Chem 100 we are really only going to look at pH and so on for strong acids and bases, because to do otherwise we would have to do equilibrium problems, and that's not till 132. If I have a strong acid like HCl, when I put that strong acid in water, I get complete ionization, and we've already talked about if HCl is 0.5 molar, then the hydronium ion concentration is always going to be 0.5 molar. So the thing to think about is this. If you're talking about an acid, the thing that you're going to get out of an acid is the H+, or the hydronium ion concentration. Okay? So if I'm talking about the kW expression, and I have the concentration of an acid like we just did, then the part of this that I will have will be this. Of course, you always know the kW, and I can find the hydroxide ion concentration. Conversely, if you're talking about a strong base like sodium hydroxide, when I put sodium hydroxide in water, I end up with one hydroxide for every NaOH. So if NaOH is 0.7, then hydroxide is 0.7. So when you talk about a base, the one that you can get directly from the base concentration is the OH minus. We have that. And what we'll be getting, we're using the kW expression, is the hydronium ion concentration. Okay? Sulfuric acid, strong acid, but it has 2 hydrogens per molecule. So if sulfuric acid is 0.6, then the H3O plus is actually, and we're making a bit of an assumption here, but we're going to stay with it. H3O plus is twice that, so it's 1.2 molar. Right, we've done this dissociation and thinking about the molarity of the species after the dissociation before. All right, so acid, I'll know this, and I can calculate the OH minus using the kW expression. Calcium hydroxide, strong base. If calcium hydroxide is 0.4, then the hydroxide ion concentration is going to be 0.8 because of that 2. I have 2 hydroxides for every calcium hydroxide. And again, base, I will know OH minus, and I can then figure out my hydronium ion concentration. So when you have an acid, you have an H+, and then you can get to pH, and so on, right? Okay, well, I have put in this handy little chart that I often draw for students when I'm tutoring them, and that is the relationships between all the different things. And essentially, the top half and the bottom half are equivalent to one another because the bottom half is the log of the top half. Okay? Now, one thing we have not talked about is how do I get from the H plus concentration to the pH, right? Well, pH is equal to minus the log of the H3O plus. So again, if I have an acid, I have a direct line to this, and then of course a direct line to this. But you can see that there are multiple pathways in this diagram. All right? If I have a base, then especially a strong base, then I have a direct path to the hydroxide concentration, which I can then either use the Kw to get H3O plus, or I can go directly from OH to POH and then use this relationship here to end up with the pH, or I can continue on with this and get the pH. So there are multiple pathways to using these relationships. When I take the log of the Kw expression, okay, I end up with 14, pH plus POH equals 14. And that's the nature of this down here. Whereas up here, it is Kw equals the two concentrations multiplied by one another. So as I said before, the bottom half is a log of the top half. All right? Now, we are going to talk about we're going to do some problems and about using these relationships. Well, let's talk about the pH scale just a little bit before we do some problems. The pH scale, again, is a log-based scale. What we have here in this diagram, and I think I want to blow this up just a little more just for the sake of looking at this diagram. Whoa. There we go. When I have a pH of 7, now one thing that's wrong here is on the left-hand side, it says the concentration of hydrogen ions, which is H plus or H3O plus, same thing. Okay, that's what they're talking about. Compared to distilled water. So there should not be a 0 here, there should be a 1. So at pH 7, I have the same concentration of hydrogen ions as that in the distilled water, in pure water. When I go to a pH of 8, I have 1/10 of what I had at pH of 7. Log-based scale means that for every unit on the pH scale, it's a factor of 10 on the hydrogen ion concentration. So once again, pH equals minus the log of the H3O plus. Of course, the square brackets mean molarity, and you'd be putting your H plus concentration in. Now, when you take small concentrations that are less than 1 and you take the log of it, you get a negative number, so that is why this negative is here. So essentially what I do is I plug in my H3O plus, take the log of it, and ignore the negative that I see there. All right, getting back to this idea of a log-based scale. For every one, so if I go from 7 to 9, that's a change of 2 on the pH scale, but it's a change of 100 on the hydrogen ion concentration. All right, same thing when you go in the other direction. So the more hydrogen ion you have, so here at pH of 0, and yes, that's possible, it is 10,000 more hydrogen ions than at pH 7. okay, and so on. So a pH of 6 is 10 times 1 unit away, is 10 times that of distilled water, okay, right? Now, on the right here are some examples of things that have those pHs, all right? So anything greater than 7 is basic. Anything that's less than 7 is acidic. So acids have very high hydrogen concentrations, hydrogen ion concentrations. Bases have much lower hydrogen ion concentrations. The pH scale is only about this. If you want to know this, then you use KW and you plug in, okay, to get your OH minus. When one goes up, the other one goes down. So if so at pH of 7, H3O plus and OH minus are equal, right? But they're no longer equal when I get away from 7. When I go to 6, the hydrogen ion concentration is 10 times higher, which means the OH minus concentration is 10 times lower. All right, so you always have that relationship. In fact, one thing I do when I do these problems is if this is 10 to the minus 14 over here, then these exponents should add up closely to 14. It just depends on what it's with. If it's 1 times 10 to the minus 7, then of course the other one's going to be 1 times 10 to the minus 7. Okay? All right, so pH scale is a log-based scale of the hydrogen ion or hydronium ion concentration. And you can look and see what kinds of materials have the types of pHs that we're talking about. Right? So pH of 0, battery acid, bad. Okay, that's pretty low. It's actually a 1 molar concentration. Do a log of 1 on your calculator. If I just take and do a log, find it on this calculator. There it is, log of 1, I get 0. So a pH of 0 is a 1 molar acid concentration. If I had a 10 molar acid concentration, take the log of 10. I'd have a pH of -1 because I'd have to change the sign. All right, so that is completely possible, and it's possible to have pHs higher than 14. A pH of 14 should be, all right, if pH is 14, then your H3O plus, of course, is very small, should be 1 times 10 to the minus 14. And OH minus is 1. All right. So if I had a 1 molar base solution, then my hydronium ion concentration would be 1 times 10 to the minus 14. If I had a 10 molar base solution, like a 10 molar sodium hydroxide solution, all right, then OH minus is equal to 10, all right, KW, so you take 1 times 10 to the minus 14 and divide by 10, and you get 1 times 10 to the minus 13 for your H3O plus concentration. Is that right? I don't think that's right. No, 10 to the minus 15. 1 times 10 to the minus 15. Okay? Now take the log of that. And you get a negative 15. I mean a 15. So a 10 molar base solution would give you a pH of 15. So it is possible to go beyond 1 to 14. 10 molar is very concentrated, but it's not impossible at all. All right? hydrochloric acid that is in the concentrated form in the bottle is 12 molar. Sulfuric acid, I believe, is in the bottle pure is, I think it's 15 molar. And I think nitric acid, these are all strong acids, I think it comes in 18 molar. I know one of these comes in 18 and one of them comes in 15. So it's possible. Very nasty stuff. Alrighty, moving on. And here's just another representation. It shows, I like this one because it shows the inverse relationship between the OH minus and the H plus. All right, so like I was saying, at pH of 0, that would be a 1 molar acid concentration, right? But your OH minus, due to the KW expression, would be 10 to the minus 14. And then the same thing's true up here at the other end of the, so see how when you add up these exponents, like right here, they add up to 14, okay? Just that when these are 1 times 10 to the minus 6 and 1 times 10 to the minus 8. If you had like 2.5 times 10 to the minus 3 and and that was your H plus and you were trying to find your OH minus, right? So if I take 1 times 10 to the minus 14 and divide by 2.5 to the negative 3, oops. You get 4 times 10 to the minus 12, okay? So this would be 4 times 10 to the minus 12. The 12 and the 3 add up to 15, but you don't have ones here, right? So try it. 2.5 to the negative 3 times 4 to the negative 12, and that should be 1 times 10 to the minus 14. So sometimes the exponents, when you don't have a 1, okay, it's not 1 times 10 to the minus 6, sometimes the exponents don't add up to 14, but it's going to be really close. Okay. All right, let's do some practice, putting into practice what we talked about, especially in terms of that diagram that have all the relationships between H plus and OH minus and pH and POH and so on. All right, now, number 1, determine the hydronium ion concentration in each acid solution. If the acid is weak because you have memorized your strong acids, indicate the value that H3O plus is less than. All right, so let's talk about that before we do any. Let's talk about a weak acid like in C, okay? C represents a weak acid, right there, carbonic acid. So if I put carbonic acid in water and I lose, let's just lose 1 hydrogen. We know we use the double side arrow for weak. So H3O plus, if this species right here, the carbonic acid, loses 1 hydrogen, 1 H plus, what is left behind? Well, if you lost a positive, you're leaving a negative behind. Okay? Just helping a 132 student with writing these equations. Never goes away. The more of them you write now, the easier it will be later. Okay, so now I cannot do the types of relationships that we have talked about so far, which is if this is 0.38 molar, I cannot say that this is 0.38 molar because this is an equilibrium. I've got a backwards reaction that's happening as well. So what they're saying here in this problem is that the H plus, the H3O plus concentration, the hydronium ion concentration, is going to be less than the 0.38. Okay, that's what they mean. So you need to know your weak acids, your strong acids, so that you know when to use this expression here, right here, because the acid or the base is weak. Okay? All right, what I'd like to do is give us a little more room on these problems. Oops. Okay, and that is going to bring us to the end of lecture 20. It says a kind of a short one, but an important one to do after we've done the acids and bases and to cement these relationships. All right, A. We have a, first of all, is it an acid or a base? It is an acid. Is it a strong acid? Yes, it is. It's one of my 6 or 7 strong acids. So if this is 1.7 molar, then the H3O plus is also 1.7 molar. Okay? Just as a reminder, H plus, erase that. H plus, I did it again. Oh my goodness. H plus and hydronium are equivalent to one another. All this is a water molecule that has accepted the H plus to form hydronium ion. Okay? Because this really does not exist alone. It's going to attach itself to a water molecule. When it does, water is acting as a base, accepting a proton. All right, B. Acid or base? Acid, nitric acid, strong, yes. So if this is 1.5 molar, then the hydronium ion concentration is 1.5 molar. All right. C, carbonic acid, not strong. Now we've already done this. So what you will do with these weak acids and bases is you will say, okay, well, because it does not completely ionize, then I know that the hydronium ion concentration is going to be less than 0.38. Over here, this is formic acid on D, not a strong acid, so I know that my H3O plus concentration will be less than 1.75. So really what they're asking here is it weak or strong? So that you can either make this assumption or you're going to have to say, pretty much I don't know, but we know it's going to be less than the concentration given. All right, so we're going to do the same thing in number 2 for bases. Basically, you're looking for your strong bases, and we are paying attention to stoichiometry. That did not come into play in number 1, however, kind of did here. So really, what we should have said here was this. If I have one of these, I end up with 2 H pluses. So I guess I could say that it's less than 0.64, but I'm going to tell you that for these weak acids, it's probably still, even though I have 2 hydrogens per molecule, it is still probably less than the original concentration of the acid. That's how little some of these weak acids and bases actually ionize or dissociate. All right. Now, but I do have two strong bases here where I do have some stoichiometry. All right. So on the first one, base, strong. So I know that the OH minus concentration, there's 1 OH for every KOH, is 2.5. B is a weak base. So all I can say about OH minus is that it is less than 1.95. In C, I have another strong base, but I make 2 hydroxides for every barium hydroxide. So instead of OH minus being 0.225, it is going to be 0.45 because it's twice this. And then D is a weak base, so we're going to say that OH minus is less than the 1.8 molar. Okay? In 3, we are given, in the top 3, we are given hydronium ion concentrations, and they want to know the other. So what is the hydroxide ion concentration giving these? And then the lower 3 we'll be doing the other way, but essentially the calculation is exactly the same because Kw equals Hydronium times hydroxide, so if I know one, I can get the other by doing exactly the same calculation every time. And that is 1 times 10 to the minus 14, working on A right now, divided by 1.3 to the negative 3. And I get 7.7 times 10 to the minus 12 for my OH minus concentration. Okay? Y'all try the next two. Pause and come back. All right, so here I get 1.1 times 10 to the minus 3. And C, I get 1.9 times 10 to the negative 11. All right, so always 1 times 10 to the minus 14 divided by the one you don't know. Scrolling. And then the last three, we're going to be doing exactly the same way, except this time we're given hydroxides, so we will be looking for hydronium ion concentrations in each case. Okay. All right, looks like 4.8 times 10 to the minus 4 for, we were supposed to also say whether they were acidic, basic, or neutral. So we'll do that here, and then we'll go back up to the previous three. We won't have to redo them, and there's a reason why. So let me finish the calculations, and then we'll talk about that. Oh. Okay, for E, I get 1.3 times 10 to the minus 13. That's not right. Sorry. Sorry, guys. This calculator is giving me troubles. There we go. 1.3 times 10 to the minus 6. All right. All right, then our last one. I get 4.8 times 10 to the minus 11. All right, now, acidic acid, acidic, basic, or neutral. It's easier since pH is minus the log of the H+, H3O+. it is really easier to look at the H plus concentration, the hydronium ion concentration, to determine whether or not it is acidic, basic, or neutral, since the pH scale is based on that. So if this is greater than 1 times 10 to the minus 7, then it's going to be acid. Because of the log-based nature of the pH scale, the smaller this number gets, the larger this number gets, the smaller the pH is. So 4.8 times 10 to the minus 4 is definitely bigger than 10 to the minus 7, so D is acid. Okay. Another way to look at it is the OH minus is less than 1 times 10 to the minus 7, so that makes it an acid. All right, H plus still greater than 10 to the minus 7 in E, so this is also an acid. Okay, and in F, the H3O plus is significantly smaller than 10 to the minus 7, so this is a base. And notice that the hydroxide ion concentration is greater than 10 to the minus 7, so that makes it a base. All right, we're going to go back up to A, B, and C, but there we were given the H3O plus concentrations for those, so we won't have to redo the problem. Okay, so A, 1.3 times 10 to the minus 3, that is greater than 10 to the minus 7, so A is an acid. B, this is much smaller than 10 to the minus 7, 10 to the minus 12, so this is a base. And in C, this number here is greater than 10 to the minus 7, so this is an acid. All right. Number 4, determining the pH of each solution. So I have been given the hydronium ion concentration, and now I'm going to use this part of our diagram where pH is minus the log of the hydronium ion. All right. So the way I do it is I say, okay, some calculators you have to press the log first, then the number. Other calculators you don't have to do that. So all different. So I say log of 2.4 to the negative 10 equals, and I see a negative there, but because of this negative here, it's like you say change the sign, so I just always ignore the negative in front. 9.62 is my pH for A. All right. And I get 1.12 for B. And I get 12.04 for C. All right. Now, number 5, calculate OH minus for each solution. There's more than one path. We can go from a pH to POH, and they take the antilog of the POH to get the OH minus, or we can, I'm going to go up on this, we can take the pH and do the antilog of the pH, which would get me the H plus, and then use the KW to get the OH minus. Okay. Either way, we have to learn how to do an analog on our calculators. Okay. So that's different on every calculator as well. Usually it's the inverse, like a second or inverse of the log key. But the thing you've got to remember is no matter which path you take is you're going to press inverse log negative 1.82 in order to put an antilog into the calculator. All right. I think that I'm going to use, let me see which one I want to use. I think I'm going to use this pathway. Okay, you can use either one. We should get exactly the same answer. All right, so I'm going to talk it through as I put it into the calculator. All right, and I need to do a little erasing here. I'll leave the other path up because it doesn't really interfere. So this is what I'll leave that up for just another little bit. All right, so I'm going to take my calculator and I'm going to say second log negative, oops, wrong negative, negative 1.82. And when I do that, I get the H plus concentration for, so I'm going to say H3O plus equals 1.5 times 10 to the minus 2. And now I'm going to use Kw to get the OH minus concentration. So I'll walk you through how I did. I went from this number to 6.666666. Okay, so I took, so after I got 1.5 times 10 to the minus 2, I said 1 times 10 to the minus 14 divided by the 1.5 times 10 to the minus 2 to end up with this hydroxide ion concentration. Okay? All right. We're going to do that 3 more times. So, oops, so you'll get used to how to, put this in your calculator. Alrighty. So for B, first thing I'm going to do is I'm going to say second log negative 13.28. Antilog of the pH gives me the hydronium ion concentration. So my first part of the calculation, I end up with 5.2 times 10 to the minus 14. Now I'm going to use Kw and do that next step. 1 to the negative 14 divided by 5.2 negative 14. And I end up with 0.192. The OH minus concentration is 0.192. All right. C, second log negative 8.29. This gives me the H3O plus. So you go directly from pH to H. You go directly from POH to OH. All right, anyway, 5.1 times, or 5.13 times 10 to the minus 9. And then the 1 times 10 to the minus 1 times 10 to the minus 14 divided by the 5.13 to the negative 9 to get my OH minus. 1.95 times 10 to the minus 6. Okay, one more. Second log negative 2.32. And I get a H plus concentration of 4.79 times 10 to the minus 3. And then I say 1 times 10 to the minus 14 divided by the 4.79 to the negative 3 to get my OH minus concentration, which is 2.09 times 10 to the minus 12. Okay, you'll of course get practice on your sapling and in your recitation, and then of course on the exam review before we have our 4th and final exam. We have 3 lectures left to go on energy and gas laws, and that will wrap up our semester of Chem 100.